And I didn't record a single bit of that. That's okay. Because right now, the people that are sitting at home, Brett and Rachel, are going, hey, Mr. Kane didn't record a single bit of the first couple slides. So here you go. Here's what the first couple slides look like. These are the gas laws we're going to be covering, these guys. Okay? And that's pretty much the other thing that I missed. These guys formed the combined gas law and studied the relationships between these gas measurements: pressure, volume, temperature, number of moles. Okay. So we're going to talk about types of relationships when we talk about the three gas laws. There is a direct relationship. Direct relationships are going to be linear, which is pictured by graph A or graph B. Graph A is linear. Graph B is also linear. The other type of relationship that exists in gas laws is inversely proportional. And the inversely proportional graph is shown by the third graph there that is labeled inverse proportion. As one thing goes up, the other thing winds up going down. Here we go. So the first gas law was done by Boyle. Or we study these alphabetically, so the first one is going to be Boyle's. Boyle's law says that temperature and it talks about temperature and why does that say number of moles? Oh, shoot. All right. Boyle basically in his experiments, he kept the temperature and the number of moles constant, so they did not vary. Okay, so he controlled for those things. And what he found is that pressure and volume wound up being inversely proportional to each other. So that when one thing went up, the other thing went down. All right, so I should explain this for the people at home. Here is the equation. P1, V1 equals P2, V2. Basically, the ones stand for before, the twos stand for after. So I'd be given information so that I could calculate a before and after situation. I'd have three of those variables if I was doing a word problem. But we don't want to do a word problem right now, right, guys? All right. Frenchman named Chuck. No, his last name is Charles. Sorry, his name isn't Chuck. All right. So Charles was a hot air ballooning enthusiast. Okay, to let you know about his hobbies. He liked to do hot air ballooning. Okay, and Charles decided that he wanted to mess around with volume of air and its temperature, which makes sense if you're thinking about a hot air balloon enthusiast, right? Somebody who wants to fly a hot air balloon wants to increase the temperature of the air, and he wants to know what happens to the volume of the air. So he made sure that he held pressure and number of moles constant. And he found that as volume increases, temperature also increases directly. Okay, so here's the basic concept. I have a volume of 1 at a temperature of, the room temperature here is somewhere around 300 Kelvin. Okay. If I double the room temperature to make it 600 Kelvin, what must happen to the volume? It has to go up, but by how much? I doubled the temperature, so what happens to the volume? It should double. Okay. All right. So the third guy is Mr. Andreu Law, and he was also a hot air balloon enthusiast. I don't know if he knew Charles or not, but he decided that he wanted to study the effects of temperature on pressure. Okay, so he raised the temperature of his hot air balloon, the air in his balloon, and found out that the pressure increases. That's what makes the balloon inflate when it gets warmer again. That's kind of like going back to that Chuck E. Cheese example we just talked about, right? Those balloons are outside, they shrink up when it's cold, but you bring them back inside in the warm air and they magically reinflate. Well, maybe not magically, scientifically reinflate. Okay, so last slide here, guys. Oh, not last slide, I want to do a couple examples. But, last slide of definitions here. When you mathematically combine Boyle, Charles, and Andreu Law, you get this gas law. It's called the combined gas law, and it's useful for solving in situations where two things are not being held constant, where three things are allowed to change, because that's more like real life. All right. Ladies and gents, this is an example of a gas law problem that I might have you do. Matter of fact, you know what? I'm not going to do it. I'm going to let... If I'm using the combined gas law equation, when I look at my things that I'm given 452 milliliters. I'm given that it starts at 22 degrees Celsius and ends at 187. I'm noticing pressure is constant, right? It says constant pressure. What that means is that I can cross out P1 and P2 because P1 and P2 are the same thing. And in this equation, if they are the same thing, they're going to cancel each other out. It doesn't matter if their value is 1 atmosphere or 101.325 kilopascals or anywhere in between. Okay, so basically I'm allowed to say volume 1 on top, 452 milliliters, divided by T1. What am I throwing in here? 295.15 Kelvin on the bottom. All right, thank you for not saying the Celsius temperature. Volume's up on top, right? So I'm going to put a V there. And what Kelvin temperature do we have here? 460.15. Okay, and that's Kelvin. So I do some cross multiplication, just like Mrs. Shopless, my 7th grade math teacher taught me to do. And we come up with a final volume of 3 sig figs. 705. What units should I put on there? All right, and that's because units in are units out. So milliliters went in, milliliters come out. Okay.